Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over some stoichiometry practice problems to show you how to use your mole ratio from a balanced equation to convert from one thing to another. So let's get into this. So so remind ourselves, let's remind ourselves what stoichiometry is. Stoichiometry is where you use a balanced equation in order to help you convert from one substance to a different substance. And the main key to a stoichiometry problem is the mole ratio that is found in the coefficients of your balanced equation. So this is where you are going to get the mole ratio. So the mole ratio between water and carbon dioxide is 2 to 4. The mole ratio between oxygen and water is 5 to 2, and so on. So you can find the mole ratio between any two substances in your balanced equation. And you can use those mole ratios as conversion factors. So you can convert from any substance to any substance in your balanced equation. So let's go over problem number 1. So I'm going to do a few problems. First few problems are going to be mole to mole. And then after that, I'm going to show you how to go from mass to mass or moles to mass using what is called the mole highway, or the conversion highway. Okay, let's get into this. So problem number 1 says, or is asking, how many moles of carbon dioxide can be made from 19.46 moles of oxygen gas. So first thing we need to figure out is where do we begin and where do we end, right? So the thing I'm always telling my students is the beginning of the question is the end of the problem. So find the beginning of the question. So here's our beginning, and the beginning is how many moles of carbon dioxide. So that's the end of the problem. Moles of carbon dioxide. So we want to get to moles of CO2. Okay, well, where we begin, that is most of the time in the rest of the question. So if you read the rest of the question, you're likely to find it there. If not, it's somewhere else in the problem, but most likely it's going to be in the question if you continue reading. So this one here, it's in the question. So how many moles of carbon dioxide can be made from what? 19.46 moles of oxygen gas. So we are going to begin with 19.46 moles of O2 gas. So we know where we're beginning, we know where we're ending, and now we're going to use conversion factors to convert from one thing to the other. So everything from here from here to here is going to be conversion factors. So we're multiplying by conversion factors. So we start always the same way we always start is we put 19.46 moles of O2. And you must have all three of these. So you have the number, the unit moles, and the substance you're talking about. All three of these you must have. This is going to keep you from making mistakes. So you put it over 1. There's no unit here. It's just over 1. So that way we can multiply by conversion factors. So if we use the line method, right, you can use the line method where you're doing this, where the next thing is going to be your conversion factor, or you can just multiply by the conversion factors themselves. Here it is. So the way I normally teach it is with just conversion factors. So I put a multiplication and then the line. Again, the line method is where you draw a line like this, which is basically your multiplication. So either way is fine, but you should use conversion factors to do this. So first thing I'm going to do is I'm going to convert this moles to moles of carbon dioxide. So I'm going to go from moles to moles. And the way you convert between moles is to use your mole ratio. And the mole ratio is given in the balanced equation. So since I'm going from moles of oxygen to moles of carbon dioxide, I'm going to use the coefficients for those substances. So I have a 5 here for oxygen, and I have a 4 here for carbon dioxide. So the ratio, the mole ratio is 5 to 4. So I have moles of oxygen here. So remember, when you're doing conversion factors, you want the moles, you want the substance here that's on top to be on the bottom to cancel out. So whatever's on top here before has to be on the bottom for your conversion factor. So since I have moles of oxygen here, I'm going to have 5 moles of oxygen on the bottom. So 5 moles of O2 on the bottom. Notice I have a number, unit, and substance. And then on top, I'm going to have moles of carbon dioxide because that's what I am trying to convert to. So here I have a 4. So that's going to be 4 moles of CO2. And again, you don't need the ES here. So you can use the abbreviation MOL. And so because I have moles of oxygen here and moles of oxygen there, that's going to cancel out, and I'm left with moles of carbon dioxide. And as soon as I have the unit and substance I want on top, I am done. So my goal is moles of carbon dioxide. I have moles of carbon dioxide, so I'm done with the conversion. So that is the only conversion factor I'm going to use. And so I put my equal sign, and at this point, all I'm doing is I'm going to multiply and divide. So I take 19.46, multiply that by 4. Everything on the top is multiplied, and then anything on the bottom is divided. So I'm going to divide by 1 and then divide by 5, and my answer that I get is going to be equal to 15.57 moles of CO2. And so this is my answer for this problem. So if I react 19.46 moles of oxygen, then the amount of carbon dioxide I will get is 15.57. So this is the number of oxygen moles that I will produce. And that's how you use stoichiometries. So it goes to using the mole ratio. That is key to all stoichiometry problems. Is the only way you can convert from one thing to another is really through the mole ratio for these type of problems. Okay, let's do another problem. Problem number 2. Okay, so problem number 2. So here we have if you made 13.42 moles of water, so same reaction. So here they're asking, if you made 13.42 moles of water, how many moles of oxygen did you start with? So here, instead of being giving a reactant and working to how much product was formed, they're giving us a product that was formed, a certain amount of product that was formed, and then working backwards to figure out, well, how much reactant did you start with to get that product? And so again, you use the mole ratio to go from moles to moles. So again, when you're dealing with these word problems, first thing you want to do is figure out where to begin and where to end and any conversion factors that you can use. So where do we begin and end? So remember what I said before. The beginning of the question is the end of your problem. So what's the beginning of the question? If you made 13.42 moles of water, right? We haven't reached the question yet. Now we're at the question, how many moles of oxygen? So that's the beginning of the question. That's our end of the problem. So moles of oxygen, we want to know how many moles of oxygen did we start with? So we want moles of oxygen. But what are we going to start with? The only other thing that we have is 13.42 moles of water. So we're going to start with the amount of water that was formed. So we're going to start with 13.42 moles of water. So now we know where we're beginning. Now we know where we're going to end. And the rest is conversion factors. We're going to multiply by conversion factors. And here, since we're going from moles to moles, we're going to use the mole ratio from our balanced equation again. So we always start with what we're given. So here it's 13. Oops. Let me erase that. So we have 13.42 moles of water. And again, I'm going to put it over 1 because we're going to be multiplying by conversion factors, and conversion factors are ratios, one over the other. So there's no unit here, just a 1. And then we're going to multiply by our conversion factors. Again, you could use the line method where you draw a line, and so this part would be your multiplication, but I like to just draw the fractions or the ratios. So here I have moles of oxygen. Moles of water. I want to get to moles of oxygen. So since I'm going from moles to moles, I have my balanced equation here. I can use the mole ratio between water and oxygen. So here I have 2 for the coefficient of water, 5 for the coefficient of oxygen. So I know that for every 5 moles of oxygen, that's going to form 2 moles of water. So I'm going to use that as a conversion factor. So since I have moles of water here on top, I want moles of water on the bottom to cancel out. So since I have 2 moles of water, I'm going to put 2 moles of water. Notice I have a number, unit, and substance. Now I'm going to put moles of oxygen on top, so 5 moles. So I'm going to put 5 moles of oxygen. And so here, moles of water are now going to cancel out, and I'm left with moles of oxygen on top. So notice that my goal here is moles of oxygen. I have moles of oxygen on top. As soon as I have what I want on top, I'm going to stop. So that's all I need to do. So using the mole ratio, now all I need to do is multiply on my calculator 13.42 multiplied by 5, and then divide by whatever's on the bottom. So I'm going to divide by 1 and then divide by 2. You don't really need to divide or multiply by 1, but my point here is like whatever's on the bottom, you're going to divide by. So if this is a 1, you would divide by 1. If this is a 2, you divide again by 2. Anytime you have something on the bottom. So you do that division and you end up with 33.55 moles of oxygen. So that is the answer to the question. So basically, if I produce 13.42 moles of water, that means I must have begun with 33.55 moles of oxygen in order to produce that amount of water. So that's how you do problem number 2. So let's go to another problem. Okay, so problem number 3 is going to be a little bit different. So in problem 3, we're not being asked to go from moles to moles, but we're being asked to go from mass to mass or moles to mass. And so how do you go about doing that? And so you'll see here, what I wrote down here is sort of what I call a roadmap. It's also, it's the conversion highway. Some people say the mole highway. So what is this saying here? So this is basically your roadmap to where you want to go from where you want to start. So just like in any roadmap, you look at your roadmap and you say, okay, I need to get to destination B and I'm at destination A. How do I get there? What cities do I need to go through? What towns do I need to take? Or what roads do I need to take? Things like that. So what places or places do I need to go through to get to where I'm going? And so this is the same way with this roadmap here. So what we've been doing so far is just converting from moles of some substance A to moles of a different substance B. And so what you see in the roadmap is like if I go from moles of A to moles of B, whatever A and B is, it doesn't matter. But if I'm going from moles of one substance A to moles of a different substance B, then in order to do that, I'm going to have to use the mole ratio between A and B. And where do we get the mole ratio? From our balanced equation. The coefficients in our balanced equation give us the mole ratio between those substances A and B, whatever A and B is. Now, you'll see that it extends further, right? So what if they give me mass of A instead of moles? Or what if they want me to find mass of B instead of moles, right? And the mass is in grams. So G for grams here and here, right? So how do I do that? Well, the roadmap tells you exactly what to do. So if they give me mass of A and they want moles of B, then what do? Is I start here and my roadmap tells me what to do. So in order to go to moles of B, I first need to get to moles of A. Well, how do I go from mass in grams to moles of A? So I have mass in grams of A to moles. Well, I need to use the molar mass of A. And you know how to calculate the molar mass by using your periodic table, adding up all of the atomic masses that of the elements and atoms in your molecule or in your substance, and then that will be the grams per mole, the number of grams for every 1 mole of your substance. And you can use that as a conversion factor to convert between moles and grams. So same thing, if I want to go from moles to grams, oh well, so once I convert mass to moles of A, now I have moles of A, and if they were asking me for moles of B, I used the mole ratio from my balanced equation, just like I did for the previous 2 problems, right? And the same thing can be happen if I am given mass of A and they want mass of B in grams. So if I'm going from grams of A to grams of B, then the roadmap tells me exactly what to do. The first thing I need to do is calculate the molar mass of A, use that as a conversion factor to convert from mass of A to moles of A. And then once I'm here, my next step to go from moles of A to moles of B is to use the mole ratio between A and B that I get from my balanced equation. And then my third step would go from moles of B to mass of B using the molar mass of B. So whichever thing they give you, wherever you start and wherever you end, the roadmap tells you exactly what to do. So let's go over this problem using our roadmap. So in problem number 3, they're asking how many moles of ammonia NH3 is formed from 54 grams of nitrogen. So first thing we want to do is figure out where we're ending and where we're beginning. So what's the end of the problem? It's always at the beginning of the question. So how many moles of ammonia? So the number of moles of ammonia is what we're trying to find. So how many moles of NH3? So that's what we're trying to find. That's the end of our problem. Where do we begin? Well, the only thing they give us in this problem is 54 grams of nitrogen. So how many moles of NH3 is going to come from 54 grams of nitrogen? So they give us 54 grams of N2 nitrogen. And here we have our balanced equation. So we know where we're going to begin and we know where we're going to end. So we're going to use our conversion factors to get us from grams of nitrogen to moles of ammonia. And our conversion factors are going to be molar mass and mole ratio. So let's start this. So we're going to begin with what we're given. So we're starting with 54 grams of N2. We're going to put that over 1. So there's no unit down here. And we're going to multiply by our first conversion factor. Well, what is the first conversion factor? Well, we got to use our roadmap. So we're given 54 grams of nitrogen. Nitrogen is our A. So we're given mass in grams of A. What's our first step? We want to get to where? We want moles of B and H3. So we want to get to here, but we're starting here. So in order to get to here, we need to first do what? Use our molar mass of A to convert to moles of A. We're going to use our molar mass. So what's the molar mass of A? A is N2. So the molar mass of A is going to be 28.01, right? So each nitrogen is 14.01. We add the two nitrogens together and you get 28.02. So 28.0 2 grams of N2 is equal to 1 mole of N2. So we can use this as a conversion factor. Since I have grams of N2 on top here, I want grams of N2 on the bottom. So I have 28.02. So 28.02 grams of N2 on the bottom. Again, notice I have the number, the unit, grams, and the substance. And then 1 mole of nitrogen goes on the top. So 1 mole of N2 on the top. So grams of N2 cancel out. Now I have moles of N2. So what's next? So now I'm here. I have moles of A. So I want to get to moles of B. So now to go from moles of A to moles of B, I use the mole ratio between A and B. Where are we going to get the mole ratio? From the balanced equation. So I have 1 mole of N2, 2 moles of NH3. So I'm going to use that as my next conversion factor. So 1 mole of nitrogen is going to produce 2 moles of NH3. So since I have moles of nitrogen here, I'm going to put moles of nitrogen on the bottom. How many moles? 1 mole. So I have 1 mole of N2 on the bottom. And so then on top, I'm going to have moles of NH3. So I have 2 moles of NH3. So 2 moles of NH3. Moles of N2 cancel out. Now I have moles of NH3. I want moles of NH3, so I'm done. So I now have everything I need. And notice I have 2 moles of NH3. That's my B. So now I'm here. So how many steps? It took 1, 2 steps. How many conversion factors? 1, 2. Then I get my answer. So when I calculate the answer, I'm going to multiply by everything on the top. So 54 times 1 times 2 and divide by everything on the bottom. Divide by 1, divide by 28.02, divide by 1, and then I get 3.9 moles of NH3. So there is the number of moles of NH3. So if I react 54 grams of nitrogen, I will produce 3.9 moles of ammonia. Let's do another problem. Okay, so here's our next problem. So problem number 4, how many grams of hydrogen are needed to produce 75 grams of NH3 ammonia? So again, first thing we want to do is write down where we need to end and where we need to begin. So as I keep saying, the beginning of the question is the end of the problem. So let's look at the beginning of the question. So how many grams of hydrogen? Stop. So the grams of hydrogen is what we want. So we want to know the number of grams of H2 that are needed to produce what? 75 grams of ammonia. So we're given 75 grams of ammonia, so that's where we're going to have to start. So we have 75 grams of NH3. So we now know where we're going to begin. We know where we're going to end. And notice that we have grams and grams. So we're going from grams of substance A, NH3, to grams of substance B, H2. So our roadmap tells us that in order to go from massive A in grams to massive B in grams, we got to go through 3 steps, right? So the first step is to convert grams of A to moles of A using the molar mass of A. So we're going to start with what we're given. So we're given 75 grams of NH3. And we're going to have to multiply by the conversion factor. So going from here to here, we're multiplying by conversion factors. And according to our roadmap, the first conversion factor is the molar mass of A. The second one is the mole ratio. Third one is molar mass of B. So we are given grams of NH3, which is our A. We need the molar mass of NH3. So the molar mass of NH3 is 17.03 because we're going to add up the atomic masses of nitrogen, which is 14.01, add up 3 hydrogens. Each hydrogen is 1.008, and you get 17.03. So 17.03 grams of NH3 is equal to 1 mole of NH3. So there's our conversion factor. So we're going to add that to this. So since we have grams of NH3 on the top, we're going to put grams on the bottom. So 17.03 grams of NH3 on the bottom and 1 mole of NH3 on top. So 1 mole of NH3 on top. And so grams cancels out. Next, now we got moles of A. Next is to go from moles of A to moles of B. So using the mole ratio between A and B, which is what we get from our balanced equation. So we're going to put our next conversion. So we need moles of A, which is moles of NH3. So how many moles of NH3? 2 moles of NH3 is produced from 3 moles of H2. So since I have moles of NH3 here, I'm going to put moles of NH3 on the bottom, which is going to be 2 moles. So I have 2 moles of NH3 and then 3 moles of H2 on the top. Oops. So moles of H2. So moles of NH3 cancel out. So now I'm here. I've used my mole ratio. Now I have moles of B, which is moles of H2. Now I'm going to use the molar mass of H2 to go from moles of H2 to mass. So that's going to be the last step. And so when I calculate the molar mass comes out to be 2.02. So 1 mole of H2 is equal to 2.02 grams of H2. There's my ratio. So since I have moles of H2 on the top, I'm going to put moles on the bottom. So 1 mole. So 1 mole of H2 on the bottom. And I have grams here, so that's going to go on top. So 2.02 grams of H2. The moles of H2 cancel out, and I'm left with grams of H2, which is what I want. So I'm done. So now all I need to do is multiply across the top and divide by everything on the bottom. And when I do that, I get 13.34 grams of H2. So that's the number of grams that is formed from 75 grams of ammonia. And that's how you do stoichiometry problems. I hope this was helpful. If you enjoyed this video, if this helped you in any way or clarified everything, please put a like my video, subscribe to my channel, share my video, hit that notification bell so you can be notified by other videos. Thanks for joining me. Have a great day.